there's one major thing we didn't get to in chapter 23, so we can spend our last time on that.
Malonic.
There you go. Okay. So we won't go through the whole mechanism here. You might try to draw the product of each step. So there should be 5 products in a row. But we won't go through all the arrow pushing.
What's the difference between the malonic and the acetoacetic acid?
For acetoacetic acid, you need to use acetoacetic thing. Unless maybe that's it, but.
If you don't see much difference, that's actually in a way a good thing, because they're the same basic idea.
Acetoacetic is a malonic, just that it has a specific name because it's the original compound.
That makes sense. Yeah.
Are you done? Oh.
Yeah.
Hydrolysis.
So where's your final product? Okay, you almost got it.
Almost.
Almost. Now notice that in this last step, we didn't just add hydronium, we also added heat. What's the role of the heat on this product?
It's gonna make the hydronium act again.
It's decarboxylation.
It's decarboxylation.
Ew.
That's right. All right, that was the only step that you didn't remember there. If you think back to the acetoacetic acid, what do you call it? The I can't remember, that other synthesis, the
Acetoacetic.
there you go, acetoacetic ester synthesis. The last step there was decarboxylation as well. Let's see if we can get that decarboxylation right. Yeah, let's talk about that. Now, let's see. So first of all, let's see how we got to where we got here. So we used the base to deprotonate this alpha carbon. We know this is well stabilized by 2 resonance structures. I like to draw the resonance structure where the negative charge is on the alpha carbon, but maybe you guys prefer to put it on the oxygen. Doesn't matter. Then we put on the methyl group with an SN2 reaction. Notice how I keep using abbreviations to save writing time. ET for ethyl and ME for methyl and PR for propyl. That can save you from some mistakes. After we put on the first alkyl group, we put on a second alkyl group with, again, turning this into an enolate and then attacking. By the way, if you wanted to, you could have left out these two steps. If you wanted to, you could only add, if you wanted to, you could have added just a single alkyl group. So it's up to you whether you add one alkyl group or two alkyl groups. Now, how do we know that this molecule is a candidate for decarboxylation?
Because it has carbox.
No, it's because, remember, it was some, it wasn't just the carboxylic acid, it was,
That's right.
A 1,3.
Yeah, that's basically right, the 1,3. The best way to put it, though, is to say that it's a beta-carbonyl carboxylic acid.
Decarboxylation can only happen
For a beta-carbonyl carboxylic acid. We don't need this beta-carbon to be another carboxylic acid, but it's got to be a carbonyl. In this case, it just happened to be another carboxylic acid, but that wasn't necessary. What we need is that it's another carbonyl.
and it will only do one, right? It's not going to blast off.
That's right, and we'll see why that is in a second. All right, and now I think one of you might have had trouble figuring out how to do the decarboxylation here. Remember, there's another video series where you can get more practice with those decarboxylations. The key is we are only going to lose the carboxy group. So the best thing is to just circle one of the carboxy groups. It doesn't matter which one you circle because they're both symmetric. Circle one of them. This might be a good candidate for the redraw and modify technique. So I just redrew the original picture, and now I'm simply going to erase the carboxy group. We're not going through the mechanism here, so all I have to do is erase the carboxy group. Now it's very important when you do that, how many carbons do you lose in a decarboxylation?
1.
Only one. A common mistake, well, you probably wouldn't make that here, but we're not going to lose this carbon. We're only going to lose the carboxy carbon and its oxygens. So this is what the decarboxylated form would look like. So this is our final product down here, and I've drawn out the methyl and the propyl group here at the end.
and so it would only decarboxylate once because now you don't have a beta thing.
Yeah, took the words out of my mouth. Now we still have a carboxylic acid, but it is no longer a beta-carbonyl. So that is why it's not going to decarboxylate. As one of you was mentioning earlier, it's not true that any old carboxylic acid will decarboxylate. Under moderate heating, only beta-carbonyl carboxylic acids are going to deprotonate. So we can get rid of one carboxyl group, but not the other. Okay, now this is what's called the Malonic ester synthesis.
Yeah.
I didn't do a very good job last time of figuring out the name acetoacetic ester synthesis. Let's see if I can figure out this one. So we can see why this is called ester, because it's got ester groups.
I think I know why.
Yeah.
Because, okay, when you have a malonic acid, it's a dicarboxylic acid with 3 carbons between. So this is malonic ester.
That's right. That's right. So if these were both carboxyl groups, the common name for that would be malonic acid. The IUPAC name, I guess, would be propane dioic acid, but it's more commonly called malonic acid. All right. So this is an ester that's related to malonic acid. Now, how is this different from the acetoacetic ester synthesis? Well, there isn't all that much difference. The only difference is, in the previous synthesis, this group would have been a ketone. In the previous synthesis, there was only one ester group. Here we start with 2 ester groups, and in the previous case, we only started with 1 ester group. Therefore, in the acetoacetic ester synthesis, we only end up with 1 carboxylic acid group. But here we ended up with 2 carboxylic acid groups. So that was the difference, but it didn't make much difference in the details of the mechanism. But that explains why the acetoacetic ester synthesis gives you an alkylated ketone, but the malonic ester synthesis gives you an alkylated carboxylic acid. Okay. So the one thing that you might find yourself forgetting again is, remember, H3O plus in heat can do a whole bunch of stuff. First of all, the H3O plus can hydrolyze everybody, and then there's the potential for decarboxylation, so we don't want to stop too soon. These videos are offered on a pay-what-you-like basis. you can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks.